Hello.
Hi, everyone. How are you?
Good, good.
Hello.
Hey. And we'll just wait a few more minutes to see who else joins.
Hello, can you hear me?
I can hear you perfectly.
Great. How are you all?
Do you have the share screen button at the bottom of your screen, or do I have to make you a host for that?
I'm gonna give it a try. So I have the share screen button and I'm just trying. How about now? Can you all see my screen?
Yeah, that's perfect.
Okay.
We just have a few more people in the waiting room that I'm waiting on, and then we'll start.
Okay.
We do. We do have several people on this call that can assess presentations. Nobody reached out specifically and let me know that they would. So if you can do that, that would be great. If you need a copy of the assessment sheet, please let me know. And I'd like to thank everyone for taking a bit of time out of their lunch to join us. This is our second time trying kind of a lunch and learn for our scheduling, and it seems to be going really well. So I appreciate you taking the time to be here, especially when it's such a nice day outside. I am hoping that we can do this in about 45 minutes. So that way, if you do have something you need to do, you have a bit more time before the hour is up. And with that, I will pass this over to today's presenter.
Good afternoon, everybody. Can you all hear me now?
I can hear you.
And then you can see my screen as well, right?
Yes.
Okay. So thank you very much for coming to my talk. My name is Kokulan, and I am currently working as a postdoctoral fellow at the Department of Plant Agriculture, University of Guelph. Today, I will be talking about the phosphorus losses from the Canadian agricultural landscapes, focusing on sources, pathways, and mitigation strategies. So this is a broad, complicated topic. So I will try to stick with some of the selected subtopics where I think they are interesting and I have done some work. Phosphorus in agricultural systems. Phosphorus is important to agriculture because it is a plant macronutrient. It is often applied to farmlands as readily soluble in organic chemical fertilizers or in the form of animal manure. Phosphorus is a limited resource as its production of chemical fertilizers often involves from mining from finite phosphorus reserves, unlike nitrogen. However, its relationship with the soil is complicated due to immobilization and phosphorus fixation. So if you look at this figure, so more than 50% of the applied phosphorus is being made unavailable by the soil, which the authors describe as phosphorus tax imposed by the soil. So this requires frequent and sometimes excess application of phosphorus to the croplands. It, in the other hand, creates environmental issues when this phosphorus reaches out the surface water bodies. So I think you all may know that phosphorus is one of the nutrients that could trigger algae blooming in water bodies. So especially in freshwater ecosystem, the phosphorus acting as the limited nutrient for the algae blooming. That means it could trigger algae blooming and subsequent eutrophication even in small quantities. So these situations lead to the loss of biodiversity, especially the local fish population. The phytotoxins secreted from the algae also decrease the drinking water quality. And this situation also leads to decrease in property values around the particular water bodies, and it also affects the recreational activities and revenue relevant to the particular water bodies. So this phosphorus pollution is a Canadian problem. So not only the larger lakes like Lake Winnipeg in Manitoba or Lake Erie and Lake Ontario in Ontario, the smaller or medium-sized lakes such as Moose Lakes in Alberta, Saskatchewan Lake in British Columbia, and Lake Ogden in Nova Scotia have been affected by these algae blooms. So this creates a dilemma. On the one hand, we need phosphorus for optimal crop production. At the same time, we do not want to pollute our water bodies. So this leads to sustainable phosphorus management. To better understand how to sustainably manage phosphorus, we need to know about its sources, the transport pathways, and potential mitigation strategies that are available for us. So let's start with the sources. So what are the sources that could yield phosphorus into the running water? The first is the phosphorus is dissolved from the soils from the standing runoff water. That is the primary pathway. And the phosphorus can also be released from the chemical fertilizers and also from the animal manure. And in cold region, especially in Canada, the frozen vegetation could also contribute to phosphorus release to waterways. And recently, the studies are indicating that the prolonged flooding generated by the extreme weather events could also be responsible for the phosphorus release to the environment. And soil erosion, obviously, and some management aspects like tillage operations and manure spreading can also contribute to increased phosphorus losses from the agricultural lands to the waterways. So let's look at some of these sources one by one. So the soil test phosphorus and on phosphorus losses. So in general, the soils with a high soil test phosphorus could yield more phosphorus losses due to their higher phosphorus content. However, this relationship can be affected by the phosphorus speciation and the hydrology of the region. So let's look at the study conducted in Canada. So the researchers here try to identify the relationship between the soil phosphorus content, here is an Olsen P, and the phosphorus concentration in snowmelt runoff as well as in the rainfall runoff. So as you could see here, there's a strong positive relationship between the Olsen phosphorus content and the runoff phosphorus concentrations in Manitoban soils. That means higher your soil phosphorus, you are going to see more phosphorus concentration in your runoff water. But this was not observed for the Ontario soils. So one of the reasons for this difference could be due to the phosphorus speciation, where most of the phosphorus, runoff phosphorus in Manitoba dominated with the dissolved fractions, whereas in Ontario, the particulates also contribute to a larger chunk of that phosphorus. And also the hydrology. So almost half of the Ontarian croplands are tile drained. So what's going to happen? This is going to increase the infiltration and percolation of the water into the soil profile, thus providing a chance for soil to buffer or filter some of the phosphorus, thus affecting the relationship. Next, we look at the effect of fertilization on phosphorus losses. So large continuous application of manual and chemical fertilizer leads up to a buildup in the soil test phosphorus, STP. Among these fertilizer and manure sources, the animal manure application, especially the swine manure application, is under scrutiny in these days. So as you may aware, the pork industry is one of the large industries in the Western Hemisphere, and most of this swine manure is being applied to the croplands as manure. So the manure can reduce the phosphorus retention capacity of the soil by increasing the labile phosphorus fractions, and also by exhausting soil phosphorus retention sites by chelating with aluminum or iron oxides. So let's see how this manure application is comparable to the chemical fertilizer when it comes to the soil test phosphorus. So in these 2-year studies, the researchers applied 4 different treatments. So 2 fertilizer treatments, F2500, F5000, and 2 liquid swine manure treatments, M2500 and M5000. And they monitored the soil test phosphorus at soil surface. So here this 5,000 applications had the double of the phosphorus applied than the F2500. So in both years, one of the typical notification is there is a high surface accumulation of soil phosphorus from the M5000 treatment. That's the manure treatment, which was applied in a higher rate. So let's also see how this accumulation from the manure treatment could be translated into the phosphorus leaching losses. So in this study, again done in Manitoba, the manure, the liquid swine manure and chemical fertilizer were applied continuously for 12 years to provide same amount of phosphorus, and the total phosphorus leached was monitored through the lysimeters. So in the first 5 or 6 years, there were no significant differences in the leached total phosphorus amount between the manure and the chemical fertilizer. But after that, we could see an exponential or increased amount of leaching from the total phosphorus, from the swine manure treatment. So we suspect that this exponential subsurface phosphorus losses from the manure treatment happened once soil phosphorus retention sites are exhausted. So not only the rate and continuity of the manure application, but also how we apply manure also matters. So most of the time we follow the nitrogen recommendation rates to apply the manure. So that means we often ends up applying or over applying phosphorus than the required or than the crop required amount. And also the form of application, whether it's a solid manure or it's a liquid manure, also matters, where the solid manure could contribute to more phosphorus accumulation. So in this study, we applied 4 different combinations of manure treatment, again the swine manure. So NLM here is nitrogen-based liquid manure treatment, PLM phosphorus-based liquid manure treatment, NSM nitrogen-based solid manure treatment, and PSM phosphorus-based solid manure treatment. So these were applied for the annual crops as well as for the perennial crops in a 3-year study. And then if you, in the start, there's not much difference in the first year after first year harvest, but after the 3rd year of harvest, you could see there's a substantial accumulation of surface phosphorus, or here the x-axis, from the nitrogen-based solid manure being followed by the nitrogen-based liquid manure. So these aspects of things should be considered when you design a sustainable manure application strategy. So the next source is the phosphorus release during the flooding events. So in a normal runoff event, what we do see is the right diagram that shows, like, first you see the ponding of water, and then you start the flow resuming from normally in normal situation from the field to the ditches. And then after the peak, they just like slow down. That means the falling runoff rates. But in extreme events, and especially in flat landscapes, you see sometimes the culverts get blocked, the streams get blocked, and what happens is water just stayed and then it increases in its stage. So these events are quite larger in their size, and they contribute to substantial phosphorus losses. So in Manitoba, we monitored 2 fields for the course of 2 to 3 years for such larger events and their impact on field scale phosphorus losses. So these flood events are like not that frequent, or that 1 to 3 times per year during the monitored period, but they contributed to more than 80% of the total annual runoff losses, and also more than 85% of the soluble reactive and total phosphorus losses. So they are huge. So the events with this prolonged flooding may contribute to elevated phosphorus losses, primarily through the large runoff volumes and increased contact time between soil and water, so that provides enough time for the soil to dissolve phosphorus to the above water column. And these higher water levels could also connect phosphorus hotspots, like in farms where the farmers try to mix these fertilizers to the runoff pathways, more concentration. And the other aspect you could see more phosphorus in the flooded water is from the reductive dissolution of iron and manganese bound phosphates, especially during prolonged flooding when there is an anaerobic condition. So during the anaerobic conditions, these IN3 plus and Mn4 plus bound phosphorus get reduced and thus release phosphorus to the standing water column. And during these larger flood events, phosphorus also could be released from the vegetation in the roadside ditches. And there are some management options that could also contribute to phosphorus losses. So research has been done on the impact of tillage on field scale phosphorus losses, but the results are a little bit contrasting. So in some regions like Canadian prairies, no-till and conservation till appear to increase runoff phosphorus losses. That's because like stratification of phosphorus on the soil surface, and also in no-till, the plant stable could retain more snow that's in runoff volume. So that could also result in more phosphorus losses. And in no-till, we do not disturb the macropore or preferential flow pathways. So when you have subsurface drainage, that's going to contribute to more phosphorus losses. However, the no-till practices did not increase phosphorus losses in regions with undulating terrain like the southern Ontario. So where you could see loamy soils with high buffering capacity and a higher macropore soil interaction. And some other management activities like manure spreading in winter infield winter-bale grazing can also contribute to higher wintertime phosphorus losses. And as I discussed earlier, the frozen vegetation can also contribute to phosphorus losses. It's been observed in the Canadian prairies where more phosphorus being lost in dissolved form from the perennial grass and forages. But the researchers did not find that kind of loss in southern Ontario. They think that even though the crops release the phosphorus, the soils has the potential to retain some of it or most of that phosphorus before it leaves outside the field. So now we talked about some of the sources that could contribute to field scale phosphorus losses. Now let's look at the transport pathways that can contribute or that kind of transport this phosphorus out from the field to the waterways. So historically, the surface runoff is believed to be the primary transport pathway for the edge of field phosphorus losses because we know that the phosphorus has a high affinity to get bind with the soil. However, the recent research has revealed that the child drainage can also transport substantial amount of phosphorus. So the child drainage is a clay or perforated plastic tubes that are buried below the ground. The main purpose of installing tiles is to keep the water table lower, so to encourage the efficient crop growth. So in Northern America, most of the agricultural lands are tile drained. In Ontario, around 45% or more than 45% of the croplands are tile drained. So why the tile drains are responsible for some significant phosphorus losses? So let me explain that with this diagram. So here we have the precipitation based on its intensity, the surface runoff is being created. And some portion of the water infiltrates the soil surface and percolates into the soil profile in two different ways. So the matrix flow is a slow process where the water genuinely percolates within the soil matrix. So this allows the sorption, desorption, and filtering processes occur. But there's also another pathway, the macropore flow, which is rapid, and that could trigger more phosphorus, or that could bring more phosphorus directly into the tile drains. So what are these macropores? The macropores are channels that are larger than 2 millimeter diameter. Examples for macropores are the earthworm burrows and also the desiccation cracks. So as you could see here, what is going to happen is macropores, they could short circuit surface runoff water to the subsurface tile drainage, overriding the soil's inherent ability to buffer or filter some of the phosphorus. So this heterogeneous flow disproportionately transport more phosphorus into the tile drains. So understanding the major transport pathway is important to implement mitigation strategies. However, the main transport pathway could vary based on the regional climate, soil type, and macropore activity. Let me explain that with two different examples. So the first one is the Manitoba, like this study was conducted in Manitoba. So the climate in Manitoba is very cold so in winter, there's a thick soil frost layer develops and it extends down to like 3 feet of depth. And that time, like the soils become like a concrete. And the soil type, the major, one of the most influential soil type in the Red River Valley is heavy clay, which has like more than 60% of clay. Yeah, there are desiccation cracks, they're big, but they immediately close when they become wet. So you have a thick soil frost layer, like when the snow melt, that's the major runoff event for Manitoba occurs, and the clays are less prone, the macropores are not permanent. So all these conditions contribute, leads to, So these conditions favor the generation of the surface runoff. In fact, more than 80% of the surface of the total runoff is occur as the surface runoff. And this surface runoff contributes to more than 95% of the soluble reactive and total phosphorus losses. Now let's move to Ontario. This was done in Essex County, Southern Ontario. So here is also the cold weather, but there are frequent winter melts, and we don't see a very thick soil frost layer in Ontario. The soil type here is clay, but there's a lot of earthworm activity. So unlike these desiccation cracks, the earthworm pores are like more permanent. So that means more downward movement of water from the surface to the subsurface. And when you have tile waves, they will end up in dry. So here the dominant pathway is the tile drainage, responsible for more than 75% of the runoff, and it also responsible for 75% of the soluble phosphorus losses and also more than 60% of the total phosphorus losses. So we talked about sources, and then now transport pathways now move to the mitigation strategies. So there's no single strategy to control or reduce the agricultural phosphorus losses. So right now, the management based on a 4R nutrient stewardship is encouraged in order to reduce the agricultural phosphorus losses. So what are the 4Rs? First R is the right source. So that matches the fertilizer type to the crop needs. And this has to be applied at the right rate. So just the amount that crop needs, and it should be applied in the right time. So when the crops need them, and also they have to be placed in the right place where the crops can effectively use them. Let's briefly look at each of these R's. So the right sources. So the examples is like readily soluble fertilizers versus slow releasing fertilizers. And then being cautious with animal manure application. And when it comes to slow releasing fertilizer, struvite-based fertilizers appear to be promising and increasing in demand. So the struvite is a recycled byproduct that is being produced by crystallization and precipitation of municipal wastewater and sewage sludge. It is considered sustainable because it's a recycled product, number one, and then it also contributes to a circular economy, and it also has other plant beneficial nutrients such as nitrogen and magnesium. And research also is looking at phosphorus leaching reduction through the application of biochar. However, further research is needed in these two areas with respect to the scale, whether it's a field scale or regional scale, and climate and soil type. Next is the right rate. So the phosphorus application based on soil test phosphorus based recommendation is encouraged. So in soils that have like higher soil test P content, so reducing phosphorus application that we call phosphorus drawdown is recommended. So let me explain that with this study conducted in Manitoba. So here it's a long-term study. So the researchers measured the runoff phosphorus concentrations from two fields, snowmelt and snowfall from 97 to 2005. You could see some increasing higher values. And after that, from 2006 to 2014, the phosphorus fertilizer was applied in limited amount, way less than the required amount. And they also monitored the runoff phosphorus concentration, and they went down very significantly. So this phosphorus drawdown could be a good source to reduce phosphorus losses from the soils that are already rich in soil phosphorus content. And obviously avoid over application of manure, and also adopting a P-based manure application could be other options. And the right timing. So avoid applying phosphorus fertilizers or manure before the major rainstorms. and also discourage manure application on frozen soils, because if the manure that's been applied on the frozen soils often just ends up in the waterways. And then understanding the sensitive seasons for phosphorus losses. For example, in Ontario, the sensitive season for phosphorus losses is the non-growing season, November from March. In prairies, that's a spring snowmelt that occurs in March or in April. And the right placement. So subsurface placement is often considered effective when compared to surface broadcast. So here this study conducted in Ontario like mimicked a winter situation. So what they used to clay soil from Essex and silt loam from St. Mary's. And there were two different application methods: subsurface banding, the dark ones, and the surface broadcast, the open circles. So what they have done is, first they rained it like did an artificial rain simulation under unfrozen conditions. So you could see, and then they measure the cumulative DRP or SRP, like soluble reactive phosphorus amounts. So when it's unfrozen, you could see like more phosphorus being lost from the surface broadcast treatment from the clays. And then they also froze the soils and again simulated a rainfall. So in that case, we noticed more phosphorus losses from the surface broadcast from both clay and the silt loam soils. And at the end, they just saturated the soil profile and then rain it over. And it is very obvious that there are like 2 to 3 times of phosphorus losses from the surface broadcast treatment from both soils when compared to the subsurface banding. And other than these 4 concepts, there are a couple of things I wanted to briefly touch, and there's a thing called controlled drainage. So in controlled drainage, the control structures or gates are installed in the tile outlet to regulate the water table level. So this controlled drainage is found to be reduced phosphorus losses due to reduced flow, and it's been reported from Ontario and as well as in Canadian prairies. And in Ontario, some studies also reported increased crop yields been adopting the controlled drainage than the free tile drains. However, you have to be mindful that controlling or blocking the tile drainage flow may increase your surface runoff related losses, and also like it can increase the phosphorus concentration from the outlet. And there are multi-purpose in-farm retention ponds being popular in the Canadian prairies, that you have a small retention pond within your farmland where the runoff water can be rerouted from the drainage ditches or from the tile outlet. One of the advantages of this can be reused for the irrigation in high water demanding periods or dry seasons. If you don't need, they can be released back to the drainage ditches on a later day where the runoff loss, like especially in the summer. However, detailed research is needed relevant to their effectiveness in phosphorus control. So one last point. Yeah, I talked about several mitigation strategies, but as you may know, there is no silver bullet, there is no single solution. So most of these mitigation strategies are dependent on the regional climate, landscape and soils and management and history. Like if you are applying manure, the history matters because you may have some legacy phosphorus with the continuous manure application, and also the cost effectiveness of the strategy. Eventually, they have to be cost effective for the farmers to adopt. So to summarize today's presentation, phosphorus is critical, is a critical plant macronutrient. However, phosphorus in agricultural runoff is mainly responsible for the pollution of many water bodies. The different sources release phosphorus from agricultural systems to waterways. However, the severity of phosphorus could vary with regional climate, soil type, management, and transfer pathways. There is no single solution for reducing phosphorus from agricultural lands. However, adopting a 4R-based nutrient stewardship seems promising. And these are the references that I used in this presentation. And thank you very much. Now I can take your questions.
Hi, it was a very interesting presentation. It's Caroline. I just have a question. How does bale grazing increase phosphorus runoff?
So I guess it's being like the bale grazing. You have the bales like brought into the middle of the field, and they just let open and then allow the cattle to graze it. So
Okay.
I guess it would increase by like the phosphorus concentration in 2 ways. Like the cattle, when it's around, they're gonna also excrete, and also there is it's still a vegetarian matter. Sorry, it's a plant matter. So what's going to happen is, like in the winter, there is going to be an alternative freeze and thaw cycles. So that means the cells get ruptured, and there's possibility for the phosphorus from this plant material to be released when you have this normal runoff water. Like many of the Manitoba, like it was reported from the Canadian prairies. So many of these Manitoba or like the prairie fields are like flat in nature, and that's the other thing. Like we are observing more flooded conditions during snowmelt, so that could provide more contact time or between this manure, they like animal manure extruded by the cattle, and also the soil and the plant matter, and also the winter water.
Okay, thank you.
I see a chat question. Have you examined phosphorus releases from applications of compost manure? I haven't examined. We are working on a study, analyzing some data, but I think like at this point I can't tell. But I guess the phosphorus release from the composted manure could be smaller than the fresh manure applications.
Do we have any other questions? Going once, going twice. All right. Well, thank you for your presentation. I always learn a lot during these presentations because I don't come from a science background, but I assume by the questions that other people definitely learned something as well. And again, I just want to thank everybody for taking some time out of your lunch to come and listen to us. If you are doing an assessment, please email it to me in the next day or two. And Dave wants to know if you can share your presentation.
Yeah, sure.
Perfect. So if you
You
two can probably exchange email addresses in the comments faster than I can organize this. But with that being said, I am going to post this video to our YouTube link unless someone emails me an objection to that. You don't need to tell me what the objection is, but if you don't want something with your name and face posted on YouTube, just let me know. And with that, we have finished a little before schedule. So I hope that everyone enjoys the rest of their lunch or carries on with the rest of their day. Thanks.
Thank you, Katie.